Today, we want to talk about integration by substitution. There is a formal technique that goes along with integration by substitution that I have not shown you. And even though it seems like I'm going to be showing you some formal technique today, I am not going to be showing you some formal technique today. I still want you to play in the playground of guess and check. I want you to think about how differentiation works, because my goal this semester in Calc 1 is to get you good at differentiation. And then next semester, we'll worry about integration. But a good way to get better at differentiation is to start trying to do it backwards. So let's think about a common question that comes up. So recall that the derivative of sine of 5x, we have to use a chain rule. It's going to be the derivative of sine of something is cosine of that thing times the derivative of that thing, which in this case is 5. So this derivative information is also integral information. So I can turn this around, and if I integrate 5 cosine of 5x dx, we'll get back to where we started. Sine of 5x plus c. This is just us taking this integral symbol and interpreting it as underderivative. This is just us understanding the relationship between multiplication and division. This first line says 2 times 3 equals 6. This second line is us concluding that that means 3 is equal to 6 divided by 2. I'm going to go the other direction. It's got some extra stuff like the weirdo notation and this plus c that's going on, but we sorted that out. The derivative of a constant is equal to 0. So when we underderivative, we don't know what constant was there that got turned into 0 by the derivative. Now we can modify this because this is this operation, this derivative operation, and so its inverse, the antiderivative operation, is a linear operator. It respects scalar multiplication. So if I multiply both sides of this equation by 1/5, I can take this 5 and shift it over so that I have the more basic formula. The integral of cosine of 5x dx. I can just divide by this constant 5 and say this is 1/5 sine of 5x. I don't have to worry about dividing the arbitrary plus c by 5 because it's an arbitrary constant. If this person figures out the plus c is 20, then this person will be calling that plus c 4. So that's not something to worry about. It's just some constant. Dividing some constant by 5 gives you some other constant. So we don't worry about that. The reason that we can do this is that we divided by a constant. And our operation respects scalar multiplication. So we didn't just divide by the derivative. We were able to divide by that derivative because it was a constant. So let's take, for example, if we have the derivative of sine of x squared, the derivative of sine of some stuff is cosine of that stuff, and then times the derivative of that stuff. So we get this 2x. This is a derivative statement. All derivative statements are also integral statements. So this is also telling me that the integral of 2x times the cosine of x squared dx is sine of x squared plus c. If 2 times 3 is equal to 6, then 6 is equal, or then 3 is equal to 6 divided by 2. The 2 part is no problem because that's a constant times our function. So it would be reasonable to say that the integral of x cosine of x squared to x is a 1/2 sine of x squared plus c. The constants we can move around. The derivative of a constant times a function is that constant times the derivative of a function. We can shift the constant, but not just the derivative of the inside. It's okay to shift the constant factors. But I wouldn't just be able to divide by 2x. So for example, if we had the integral of cosine of x squared dx, I couldn't just say that this is sine of x squared plus c divided by 2x. We can't just divide by the derivative of the inside because the derivative of the inside is not just a constant. This is not a valid move. So when we have the integral of x cosine of x squared, 1/2 sine is 1/2 sine of x squared. That 1/2 is because we can get rid of constants. We can move the constants around, but we can't just divide by the derivative of the inside. If we think about the derivative, this statement says that the derivative of sine of x squared over 2x is cosine of x squared, and we know that that is not the case. If we find the derivative of sine of x squared divided by 2x, this is not going to end up with cosine of x squared. We'd have to use the quotient rule, which says take the derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom squared. And all this is clearly not going to be cosine of x squared. Any questions? What we want to be on the lookout for, like we pointed out yesterday, is an inside and the derivative of the inside as a factor. This is the combination that we're looking for. Inside and the derivative of the inside. Any questions? The other thing I want to reinforce here is that when you found what you think is the antiderivative, if you take the derivative, you should get back to the start. That's why we call them derivative and antiderivative. So if you find an antiderivative, you should be able to derivative your way back to what you started with. The derivative of sine of x squared is cosine of x squared times 2x. Going back. The derivative of 1/2 sine of x squared is 1/2 cosine of x squared times 2x. The 2 cancels out with the 1/2 and leaves x cosine of x squared. So it worked out. Any questions? We're doing this not because I want you to use the formal technique with all the steps of integration by substitution. We're doing this because I want you to be better at finding derivatives for reasons. How's everybody okay? Of course we're okay. It's Friday. No one's going to ask questions today, especially not when we're past halfway. It's like, oh, no. We're half of a calc class away from freedom, the freedom of the weekend, where I can put everything off until Sunday night. It's always amusing when I hear students talk about how they're going to catch up over the weekend. And then the first thing, every time I hear that, I think in my mind, first thing I think is, no, you're not, but it's adorable that you believe that. For some of you, I guess it's totally true. So you're like, I don't know what you're talking about. I'm going to get caught up on Sunday morning and get up early and get my work done and have the rest of the day. But some of you know exactly what I'm talking about. I'm going to get caught up I'll get caught up over the weekend. And then on Sunday night at 9 o'clock, I'm like, oh, well, I guess I better get started. I've got a paper due 2 days ago, so I better get started on it. I mean, ask me how I know. That's how I did all my papers. It's true. Depending on what general ed class I would have to take, I'd go to all the different professors that were offering that particular class, find out which one had the shortest paper requirements, fewest number of total pages, and also fewest number of projects. Like if 2 classes were both going to be 50 pages of submitted work required, one of them was like one 50-page monster, and the other one was like 5 10-pagers, it would be hard to decide. I might go for the one thing because then you just have to do one big project. But there's a threshold. If it was going to be 10 5-page assignments, I would probably pick that one, even though it's like a huge number of things that I'd have to do. They're all almost trivially short. See how it works? 1 50-page versus 2 25, no question, do the 50 because there's only one. 25 is ridiculous. Doing that twice, that's double ridiculous. 150, that's just one ridiculous. But 10 5s, that's 10 like borderline trivial. So I'm like, I will take that one. Even if there were more, even if it was like 12 5s, I'm like, I'll still take that one, even though it's technically more pages. See how it works? This is student calculus. I don't know how much in your high school, I don't know how much student calculus you had to do. I don't know if you know this, but you all automatically do calculus. You do like this engineering calculus, no problem. You do it without thinking about it. I mean, you just instinctively know how to do it. If you've got 2 people on a collision course, right? First of all, if you're in this situation where there are 2 people, just by looking at where that person is, their position, how fast they're walking, their velocity, and whether they're walking at a constant speed or not. Let's just assume that A and B are both walking at constant speeds. You solve this problem. You solve this system of equations, and you both conclude like, oh, we're going to walk into each other if we continue on this path. And so what do? You trade in your system with constant velocity by starting to adjust your acceleration. You trade it in for a system of differential equations. And you do this on the fly. You're like, I'll slow down a little bit. You just apply a little bit deceleration. Then you see the other person applies deceleration. You're like, oh no, we're now we got the system of problems going. If they don't notice you, it's a little bit easier, right? If that person, person B does not see you, it's easier for you because you just have to slow down or speed up. You don't have to worry about what they're doing. They're on their phone. You just speed up and go in front, or you slow down and let them pass, right? But if they see you and they start making adjustments as well, now we've got a different system of differential equations. Because now you're adjusting your acceleration, they're adjusting their acceleration, you slow down, they slow down, you speed up, they speed up. And eventually you have to do the one thing that solves most problems that we try to avoid is communicate. Like, oh, sorry, excuse me, why don't you go on ahead? You know what I mean? This is why you shouldn't tint your side windows in your car. I don't care how cool you fucking think it looks. You are reducing the amount of communication that you can participate in. If you have tinted side windows, don't sit there and expect me to cross the street. If I can't see your face, I am not walking in front of your damn car. Just know. If you don't have tinted side windows, I can look, I can see that you've seen me, and I can identify that we've communicated. So now I'm like, oh, now if you hit me, there will be malice and violence can ensue. But if I don't know, I'm just waiting. I don't care if I'm going to be right when you hit me with the car. I don't care that when we go to court, I'll be able to sue you. I'd rather not get injured in the first place. So if you have tinted windows, I'm just going to wait there. I don't care if you're looking at me. Roll your fucking window down and say, go ahead. Because until then, I'm just waiting. There's a reason it's illegal to tint your side windows, because it reduces your ability to communicate with pedestrians and other drivers. And that's what we need to do when we're out there driving. It's a cooperative thing. You're not driving your car. We're all driving together. Do you know what I mean? That's a long way from this, but it brings me to my next point. Look how good you are already at calculus. You're driving up to a corner, you know how much you need to slow down. You know how much you need to turn the wheel. You know when you can start accelerating. You know if you're driving a different car, what it's capable of doing. And you have to translate this through a machine that you may have just started driving that hour. And so you just like test the brake a little bit. Oh, this car will do that. You test the accelerator a little bit, this car will do that. You know what I mean? And then you can make these decisions. You can do this while looking through a mirror and traveling at 60 miles an hour. Because you're getting on an on-ramp, you check your mirror, you see a car coming up, and you can tell how fast they're going. And if they're going to accelerate you and you need to come in behind them, or if you can accelerate a little bit more and go in front of them. You once again do this complicated problem through a mirror. You know what I mean? It's like in the Westerns, when the cowboy pulls his gun out, turns his back on his opponent, pulls the mirror up and tries to shoot the dude through the mirror. You do that in a car at 60 miles an hour. That Western dude is just standing there. And he's usually at a range where the bullet's going to travel pretty much straight anyway. So not impressed. Getting onto a freeway, that's pretty impressive engineering piece. Any questions? Not about not walking into people, but yes. This one here. So the question was, it kind of stems from this example up here. Integral of cosine of 5x is 1/5 sine of 5x. And that 1/5 is to compensate to get rid of the derivative of the inside, because the derivative of the inside of 5x is going to be a 5. I want that to cancel out because I want a 1 up in front of my cosine, right? So I got to cancel out the 5 from the derivative. I got to cancel out the 5 from the derivative, so I just divide by the 5. That only works when it's a constant. So here, I got to cancel out the 2x from the derivative. So I'll just try to divide the 2x because I need just a 1 up in here. But that's not a valid move because the derivative of the inside wasn't just a constant in this case. We can't just divide by the derivative if it's more than a constant. So that's why I said this is not a valid move. Dividing by the 2 up here, that worked because all I needed to do was cancel out a 2 to make this a 1x instead of a 2x. I can trade my 2x for a 1x just by multiplying by a half. I can't trade my 2x for a 1 by dividing by the 2x. So we're demonstrating that this is not a valid move by taking the derivative of what we thought was our integral, realizing that we had to use the quotient rule, and came up with something different than cosine of x squared, which is what we wanted to get. So that was the point of that last example. No, this is demonstrating that this technique will not work. So this is showing us that this is not a valid move. This 1/2, no problem, right? The derivative of a half of the sine of x squared is a half cosine of x squared times 2x. The 2's cancel, leaves x cosine squared x, cosine x squared. That's what we wanted. Didn't work here. I couldn't just divide by the 2x. Because now to take the derivative of our antiderivative, we'd have to use the quotient rule, and it does not get us back to cosine of x squared. No, not down here because we're taking derivatives. If we put a plus c up on the sine of x squared, the derivative of that term is going to be 0 anyway, so I didn't worry about it. Or I could just say, here's an antiderivative that won't work. So I'll choose the one where c is equal to 0. It doesn't work when c is equal to 0. It won't work for any other c. Any other questions? Is everybody okay? No. I know it's weird. I make fun of your arithmetic skills. I make fun of your algebra skills. I make the claim that you don't even understand counting. And yet, I still believe that you can do calculus instinctually. Just use your instincts on calculus. Position, velocity, acceleration, adjust that stuff on the fly in real time. No one's even tried to explain how counting works. All right, that's going to do it for this week. We'll see y'all on Monday. Have a good weekend, and thanks for playing.